So any object that can be deformed. So a golf ball when a club hits it, a baseball when a bat hits it, uh, a slinky, right? We can stretch it, we can compress it. Anything that can be deformed and then return to its original shape. That's key. If it's deformed and it stays deformed, that's not elastic potential energy. But if it deforms and returns back into its original shape, it's said to have elastic properties. Okay? So items with elastic properties include elastic bands, the pole vaulter's pole until it snaps and then it no longer has elastic properties, springs. And what we see is this concept. Here's the original spring shape, okay, original position. So whether it's a baseball or a golf ball or a pole vaulter's pole or an elastic band, it has an original shape. So you're going to have an original shape, and then you can have one of two ways. We can stretch it out, or we can compress it. Okay? This is stretched. I think I spelled that right. And this is compressed. Both of these, so it has stored potential energy. And then what happens is we go back to the original position. Or here's a more scientific term, we reach equilibrium. Okay? So again, a slinky just sitting here minding its own business. This is stored. And if I was to squish this, if it was plastic, I could get it to go even closer. Okay, stored potential energy. When it's deformed, it has stored energy until it's allowed to bounce back. And that whole piece where we stretch it and then let it come back to its normal position, that's what we call elastic potential energy. Okay? We can calculate elastic potential energy. Elastic potential energy can be calculated using a potential energy formula that involves half of K, which is a spring constant. The spring constant has to be given to us. It's not a one number for everything. It depends. And then X is the amount of expansion or compression in meters. Okay, so EP equals 1/2 kx squared. And if we look in our data sheet, it should be there. If you look under momentum and energy on the bottom left of your data sheet, under momentum and energy, everybody should have their data sheets out. You will find the potential energy for spring. E equals 1/2 kx squared. Okay? Out of all of the work that was done, somebody had to investigate this. And it happens to be a guy named Hooke. And he said that force is needed. You have to apply a force to expand it. You have to apply a force to compress it. Is needed to expand or compress it depends on the amount of expansion. So this little bit of expansion on this slinky is not going to require the same amount of force as if I had expanded it like this. This is what it's at, then I would really have to push it in. Whereas if it's just like this, I have less distance to travel, so less amount of force. Okay, so that's Hooke's law. Force is dependent on how much expansion or compression there is. So now we're adding in another force. We have force applied, force friction, force normal, force of gravity, centripetal force, and now we have the force of a spring. Okay? K is the spring constant and X is the amount of expansion or compression. K varies for each type of spring and is measured on how stiff it is. The larger the constant, the stiffer the spring. So these kinds of springs we would find in heavy equipment. You don't want something like a hydraulic crane that's moving timber across a lumber yard to have lots of bounce and give in it. You want it to be stable. So it's going to have a heavier spring made with probably like an iron ore, as opposed to your car. You don't want your car springs to be ramrod stiff when you go over those bumps. You want there to be a little bit of give. You don't want there so much give that you're like a low rider going across the Dunvegan Bridge, but you need a little bit of give. Okay? Negative sign in the formula implies that the force pulls back. So if you see this, it's Fs is equal to negative Kx. This sign is important. Okay? The force is often referred to as a restoring force. So a restoring force is what does it take to put it back to its original state. All right? Let's look at an example. The force of 37 newtons is required to stretch a spring 20 centimeters from its equilibrium position. What force is needed to compress the same spring 7 centimeters from its equilibrium? So first, let's start identifying information in this question. What's one piece of information, Avery? Okay, so it's a spring, right? Because we had to stretch it. It is the same concept as force applied, but we call it the spring force. Cameron, another piece of information. Okay, so X is 20 centimeters. That's the first time that we look at this being stretched. Daniel, a second piece of information. We compress the same spring. That's important. So we know that the K is going to be the same from this distance here, 20 centimeters, and this distance here of 7 centimeters. Princess, the fourth piece of information. Seven centimeters is the second distance that it gets compressed to. Okay? And so it's asking us what force is needed to compress the same spring. So in order to solve that problem, force spring is equal to negative Kx. Okay? And we're looking at x2 because we're looking at this 7 centimeters. Now this is what we're being asked to find. We have the x2. Do we have the k? Why are we looking at this x2? Because it's saying what force is needed to compress the same spring 7 centimeters. So that's the second distance. Okay? Do we have K? No. Can we find K? Yes, we can, using the exact same formula. Force spring is equal to K, negative K, x1. If we use the first spring, because we have force of the first distance, and we have that first distance. And so then negative K is equal to force spring over x1. And we get what value? Note that I already converted the distance. You cannot use the 20 centimeters. It has to be 0.20. Okay? And I can solve for the original question, which is the spring force when it is compressed to 7 centimeters. So I'm going to have negative times negative 185 times 0.07 centimeters. And my spring force is then what? Okay? Now, is force scalar or vector? Which one, Joyce? Starts with a V and ends with an ector. It's vector. So my force not only requires significant digits, but it requires a direction. And when we go back to the question, what force is needed to compress this same spring 7 centimeters from its equilibrium? So we want to put it back. Okay? If we were stretching it, we could say out if you wanted, because it's going outwards. Okay, looking at this one. A spring constant of 55 newtons per meter has a 450 gram mass suspended from it. The spring is attached to a ceiling as shown in this diagram. Draw a free body diagram for the stationary mass on the spring and then determine the extension on the spring. There's quite a bit of information in this question. The first one being this one here. The word suspended. If something is being suspended, is it in motion? Is there an acceleration? No. If something is being suspended, that is code word for force net is equal to 0. Okay? And then, so the first part says, draw a free body diagram for the stationary mass. Well, the spring is hanging like this. It's just hanging. So gravity is working which way? Which way? Down, right? Down towards the center of Earth. So the force of the spring, stop moving, must be working in which direction? Up. It's the opposing force. This is not equilibrium for this slinky. This is equilibrium for the slinky. When I set this down like this, it doesn't separate out. This is not equilibrium. So there's a force that wants to bring it back up like this. Okay? So we have force gravity, spring force. So it says determine the extension of the spring. First, let's identify some information. We have a K value of 55 newtons per meter. That's the spring constant. The spring has a mass of 450 grams. Pay attention to units. And it's asking us to determine the extension of the spring. The extension of the spring simply is another code word for how much is the distance that this spring is stretched out. Okay? So how do I solve that very original question? Determine the extension of a spring. Well, we know that if we're looking at forces, two different forces here, we would have force net is going to be equal to force gravity. Whoops, wrong one. Oh my goodness, Mrs. Pyre. Plus force gravity, sorry, the negative force of gravity. This is force spring. Let that dry. We know that force net is 0, so that means that the spring force must be equal to the force of gravity because it's just hanging there. It's not doing anything. It's just hanging there. It's not stretching and it's not going back up. So how do I find force of gravity? What's the formula for force of gravity? Mass times what? Gravity. Mass times gravity. How do I solve for spring force? Kx. And we're being asked to solve for x. So then x is equal to mg divided by k. Okay, so when I go to solve for that, x is equal to 0.450 because we're going to make sure we convert to kilograms, multiplied by 9.81 meters per second squared. This is kilograms. Divided by K, which is 55 newtons per meter. And so X is equal to what value? Okay. So X is equal to negative 0.08026 and carrying on with decimals, kilograms. No, not kilograms, meters. Before we go into significant digits, let's look at the unit analysis on this. The unit for the 450 grams converted is kilograms. Then we multiplied it by acceleration. And then we divided it by a Newton divided by a meter. What do we know this unit to be? Kilograms, meters per second squared are the base units for what main unit? Newton. So these two pieces here, cross this off, and you're left with 1 over 1 over m, which is equal to m. So that's how we do a unit analysis, and we know that this x is a meter because we follow the unit analysis. We don't even need a formula. We just need to look at the units. Okay, significant digits for this question is? Okay, so what are my significant digits for this? So 0.080 meters is perfectly fine. Or we could do 8.0 centimeters. 6 of one, half a dozen of the other. Because it was reported in grams, chances are centimeters would be the unit that they would go with. But this is the base unit for physics, so this is 100% acceptable to me, the meters. Now, what do we do about the negative sign? Avery pointed out the negative sign in the formula. What does that negative sign tell us? The negative sign tells us that that spring is being compressed. Okay? Not expanded. The force, it wants to bring this back to normal. It doesn't want to come like this to get to equilibrium. It wants to do that to get to equilibrium. Okay? All right, one more question. The amount of stored energy in a spring is 19.0 joules. If the amount of expansion or compression was reduced to 1/2 of its original value, what will be the new stored energy of the same spring? This is just a relationship question. So here's my original, and it says that my potential energy, so EP is how we write a potential energy, is equal to 19.0 joules. If the amount of expansion or compression was reduced to 1/2, well, first let's look, how do we solve EP? What was the formula that we learned on the very first page? Okay, so then if I look at my modified, it says that the amount of expansion or compression, which is X, is 1/2 of its original value. What will the new stored energy be? Okay. Well, we know that E prime is going to be equal to 1/2 K 1/2 of X squared. And so when I write that out, EP is equal to 1/2 K X squared, because I squared the X. If I square 1/2, I get what? 1/4. So all I'm doing is I'm pulling out the numerical part separate from the formula, because this looks like this. And so then I could say EP prime is equal to 19.0 joules times 1/4, which would be what? Okay, 4.75 joules. That's what E prime is going to be. That's the new modified energy.